Well, welcome everyone. Thank you for joining us. My name is Ben Margalit. I am a postdoc at UC Berkeley, and it is my great pleasure to chair this session. I'm really excited to hear what we have from all of the speakers. So this is the first session, session A of panel plenary 6. And in this plenary, we'll hear about multi-wavelength searches and counterparts to FRBs. Something very near and dear to my heart. So I'm really excited for all of the upcoming talks. If you do have, as a reminder, if you do have any questions, please put them in the Q&A. I'll be monitoring that. I'll also keep an eye out on the Slack, but I may not be as diligent about noticing things on Slack. If any of your questions aren't answered in real time or you have questions later on, please do put those in Slack. I'm sure the speakers will be very happy to chat and discuss their work and answer any questions on that medium later. All right, so without further ado, let's get started. First off, we have Charlie Kilpatrick from Northwestern University. He'll tell us about constraining optical counterparts to FRBs. And take it away, Charlie.
Great, thank you so much, Ben. Yeah, great. Okay, I'm really excited to be here, and thank you so much to the conference organizers for putting this together. I feel like I've learned a lot, this being my first, big FRB conference, and there have been a lot of great talks so far, especially on the radio side. But I'm very honored to be able to kick off this multi-wavelength session and tell you a little bit about the work that I've done as a postdoc at Northwestern University and in collaboration with the F4 collaboration. But I'd also like to recognize that we wouldn't be able to do this work without really the great scientific input from FRB collaborations like Chime and Craft, and some of this work was done in collaboration with both of them. So without further ado, this is specifically on optical counterparts to FRBs and constraints on transient counterparts. So we've heard a lot about this, and I won't really belabor, why multi-wavelength too much, but as we've heard multiple times now, radio bursts are cheap. And there's a rich body of literature just describing all of the many progenitor systems, and in particular emission models that can cause these. But the counterpart models at shorter wavelengths can vary wildly. And so I think that gives us a lot of great leverage on what progenitor systems, and again, emission models exactly are producing the radio bursts. And that's really the kind of angle that I like to look at FRBs from. And of course, we've heard as well that there might be multiple populations of FRB progenitors. They span a very wide range in injected energies and luminosities, and just the environments and distances at which we've seen FRBs, all the way from the galactic magnetar, of course, to the most luminous and distant bursts. So I'd like to think just about all the possible progenitor models and what counterparts they might have. And I think just looking at this large population as a whole, and constraining what counterparts we can, even if some of them are intrinsically rare, can give us a good angle on really getting to the bottom of this progenitor problem. And just going in a little bit deeper into the galactic magnetar, sort of our forlorn hope is this X-ray counterpart that we've seen both in integral and CONUS wind. That's also been discussed. But this also tells us a lot about what we might expect to see at other wavelengths, and in particular the optical. So of course we've heard about the synchrotron maser, which predicts some emission in the optical. Magnetars, as we know, come directly from core collapse supernovae, which, despite the fact that G57.2 is likely over 10,000 years old, of course, supernovae produce the luminous optical emission and perhaps persistent emission long after that. And so, we'd really like to constrain at all time scales, and in all ways what counterparts we might expect to see. And so the optical provides really a rich body of literature in theory and observations, and in particular of sources that we know are counterparts to neutron stars like short gamma ray bursts, kilonovae like we've heard about in the previous sessions. Not shown on here are fast blue optical transients and luminous red novae, all sources that we might expect to be associated in some way with FRBs. And so this is really my goal, is to be able to constrain at all time scales, and in particular these very short time scales, what we might expect to see right before or right after a fast radio burst occurs. So there's really three strategies that I've tried to organize this into in ways that I think about constraining these optical counterparts to fast radio bursts. A lot of people have looked into coincident imaging just in really the large amount of survey and archival data that we have, just because optical surveys are conducted all the time and image the entire sky down to relatively faint magnitudes every night. And these, of course, can constrain bursts on timescales, or optical counterparts on timescales of days to years of a burst. So getting to these more slowly evolving counterparts. I'm also engaged with more reactive follow-up. So immediately succeeding a burst, we've been able to trigger follow-up on timescales of minutes, and extending to within days of a burst, which again can constrain some of these same counterparts, but getting more into the regime of the extremely fast varying optical counterparts. And then, of course, the vast majority, I think, of the multi-wavelength follow-up has just been pointing at repeaters, and that's yielded a lot of the most interesting scientific results that I'll get to a little bit at the end. So thinking about these coincident sources or coincident imaging and survey data that we've been obtaining just all the time in the optical. So the transient name server, which mainly catalogs optical transients, but it now, of course, is cataloging a lot of the chime sources, is a great repository of well-known bona fide optical transients. And in the future, surveys like the Large Synoptic Survey Telescope is going to obtain a lot of data and really dwarf the size of these catalogs, and enable us to associate possibly optical counterparts with fast radio bursts that are occurring every day, like in the chime catalog. But you know, I've been wanting to think about just you know, what is the best strategy to use to perform these associations, as it was done recently, just using the Zwicky transient facility with the repeating FRB 180916 and looking at coincident optical transients. And you know, really, this is sort of a numbers game where better localization and time constraints can give you a handle on what optical counterparts like supernovae and these fast blue optical transients might be associated with bursts. So just as an exercise, I've been taking the entire chime catalog and cross-matching to sources in the transient name server, and doing this with a graduate student at Northwestern, Vic Dong, who's really becoming an expert at this. But even with the relatively coarse localizations that chime has, we're able to you know, very precisely say that only a handful of optical transients could be associated with these bursts. And even beyond that, in F4, we're using the dispersion measure constraints in conjunction with the Marquardt relationship, and in work similar to that that's been done in the past with F4 to be able to constrain the likely volume in which these bursts are happening. So even further narrowing down what optical transients could be associated with bursts. So you can imagine doing this on the fly with every single burst that occurs in the future and with a very large number of transients that are going to be discovered, for example, with LSST. But of course, really the problem here is the probability of chance coincidence. And of course, it's impossible for both of these transients to be associated with the FRB. So, what do we really need to be able to say just on the fly, what is an optical transient that we really think with high probability is associated with a burst? Well, just with an on-the-fly equation and calculating the supernova rate within sort of this volume that I'm using for a chime-like burst, we would expect about 55 supernovae per year per degree squared. So getting our localizations down to about 1/10 of a degree squared or better, as I knew a lot of groups are already doing or will soon be capable of doing, will yield exponentially better association between the large body of optical transients that we'll soon have and the FRBs that are being discovered every single day. So just moving on to the more reactive or follow-up that we've been doing in F4, we've been using a lot of telescopes all around the world to perform rapid targeted follow-up. And of course, this is difficult because it's hard to get onto a telescope, on the timescales that FRBs occur over milliseconds. But with follow-up on the timescales of minutes to hours, and especially using the FRBs occurring in the local universe at low DM, as we're finding more and more of, we'll be able to constrain these fast blue optical transients, kilonovae, neutron star-like counterparts, as well as the sort of luminous red nova models that I'm hoping we'll hear a lot more about in a future talk. But to hear more about this and the follow-up that we've done so far, I really encourage you to look at Consuelo Nunez's poster on follow-up that we've done of 8 FRBs on sort of short to moderate timescales. But we currently have a program now using Las Cumbres Observatory, and we're trying to get this follow-up down to within minutes or even faster to seconds using rapid TO time. And that's really possible because Las Cumbres Observatory, of course, has global coverage. And so an FRB in principle that occurs anywhere in the world, especially say in Canada or Australia, where a lot of our searches are occurring, will have coverage on the ground in the immediate aftermath and can slew a telescope immediately. And we found that we can get follow-up within at most 5 minutes of a burst. But to do this effectively, we really need a reaction system and rapid alerts, so low latency alerts via events that we'll be able to react to on the optical side.
Charlie, 3 minutes.
Okay, great. So finally, I just like to talk about really, I think where some of the most promising follow-up has done. So pointed monitoring of repeaters, and especially our favorite repeater, FRB 180916. We've been able to obtain a lot of lucky observations like we did last year, almost exactly a year ago, with the 4-meter APO telescope, where we obtained follow-up within 2.2 seconds of the burst as we were basically just sitting on it. And so these provided some of the deepest constraints on a synchrotron maser counterpart. We were able to rule out significant parameter space just down to extremely deep magnitudes using this 4-meter telescope on second timescales. But stay tuned to the next talk to hear about very interesting constraints on even shorter timescales using a larger aperture telescope. So we're able to rule out, for the synchrotron maser model specifically that I think is very promising, parameter space just using this one very lucky observation. And so I think this is a promising method, especially again with these low DM bursts, where we'll be able to say, is this model consistent with what we're seeing? There are a lot of caveats to this based on the size scales and where the source of the emission is exactly. But I think this is going to be probably the way of the future for, at least for optical follow-up. And then finally, I know this is an optical talk, but we're continuing this sort of lucky monitoring follow-up, just sort of pointing and praying with NuSTAR and XMM Newton on September 14th and 15th. This will be the most sensitive hard X-ray observations to date of FRB 1809-16. We welcome collaboration from anyone, especially with radio follow-up, but really any multi-wavelength searches that want to perform observations on these dates with us. And so with that, that's the end of my talk. I'll just throw out my conclusions and take any questions.
Thank you, Charlie. Thank you for that wonderful talk. Great. So we already have one question. Please do, as a reminder, ask more questions on the Q&A and or the Slack. So first question is from Liam Connor. So Liam's asking, for the CHIME FRB localizations, do you convert the provided confidence interval arrays into likelihood functions and marginalize? Or do you just ask which optical transients fall within, say, 68% confidence limit?
Yeah, so we're just using, these are the heel picks provided by CHIME, so the exact confidence interval. And here I've just taken, I think it was the 90% confidence interval. Of course, our grad student, Vic Dong, is writing this in a way to be sort of flexible and that we can perform on the fly with any kind of confidence interval. So, you know, whether you just model it as an ellipse or we have one of these heel picks maps. But here, yes, it was somewhat arbitrary that I just took the 90% from what was provided.
Great, thank you. And then we have another question from Brian Gensler. So Brian asks, have you looked for historical supernovae that occurred years or decades before the detected FRBs?
Yeah, so I think that's really the merit of using the transient name server, is that actually all of those supernovae, so going back to, you know, the ones in Zwicky 1954, or, you know, even earlier, the supernova discovered in Andromeda in the late 19th century, all of those supernovae are in the transient name server. So in principle, as long as you're using the right database, then you can cross-match to any FRB. And we've done that and found a few hits going back decades, but you know, this is still work in progress. And so we need to really vet these just based on the analysis that I've described here.
Beautiful, thank you. All right, I'll wait one more minute if we have any additional questions. Someone is typing. All right. Well, if not, you can continue asking questions on the Slack channel. Thanks, Charlie. That was a wonderful talk. And now let's move on to our next speaker. So next up, we have Nicolas Tejos from Universidad Católica. And Nicolas will be telling us about high cadence optical limits on a particular repeating FRB 1809-16. So take it away.
Thank you. Can you see the screen?
Yes, there is a bar. Oh, now I can see it perfectly. Yeah.
Okay, so thank you very much. Hi, everyone. I am Nicolas Tejos. I'm a professor at Universidad Católica de Valparaíso in Chile. I'm going to be presenting results on high-cadence optical limits on the repeating FRB 1809-16. This is work done in collaboration with CHIME, but as part of the F to the 4th team. And in particular, I highlight here the contribution of Prochaska, Consuelo Núñez, and Charlie Kilpatrick for these particular observations I'm gonna present. So yeah, the outline of the talk is the following. I'll start with a brief motivation. Then I'm going to present the experimental design and the particular observations we use. Explain the target a little bit, why we chose it, the optical imager we use, which is called Alopeke in Gemini North, that reaches 10 millisecond timescales in the optical cadence, and also comment about the time coincident poles during the time of the optical observations. So the results, I'm going to present briefly the results, which are non-detections of optical counterparts from which we can place upper limits that might be interesting for constraining theoretical models, which I briefly mentioned in the implications. I'm going to finish with a summary and conclusions. So the main motivation is, of course, have observational data that might be able to constrain theoretical models for the engine mechanism of fast radio burst, and in particularly to perform high cadence millisecond optical follow-up of fast radio burst. As has been nicely reviewed in the last days, and also by Charlie in the previous talk, there are several models that predict emission at shorter wavelengths than radio, and that includes the optical. Some of these models are synchrotron masers or magnetar flares, but there might be others as well, and depending on different models, predicts different intensities of the optical counterparts. However, as far as I know, no associated optical emission has yet been observed, and this corresponds to timescales of seconds, days, months, or years. And of course, those searches are also subject to small samples and strong selection biases. But still, people have been looking for optical counterparts and none has been found so far. One of the main problems in the optical searches is the cadence of the observations, because even the shortest ones, like seconds, that we are used to in the optical community, at least in the extragalactic optical community, is large compared to the millisecond timescale of the FRB pulses themselves. So perhaps a new alternative for continuing this optical monitoring is to go to the millisecond timescale as well. And that has been done, for instance, in the past by the work of Hardy et al. 2017. However, those limits were not constraining because of the FRB that they chose to follow and the optical aperture that they used. So the question remains whether there are or not optical counterparts, and we want to try to answer that from the millisecond timescale perspective. So the experimental design and the observations, we will closely follow the work of Hardy et al. 2017. They observed FRB2011 with the 2.4 meter telescope, Thai National Telescope, and the ultra-spec instrument, which reached a cadence of 70 milliseconds. So we want to repeat the same experiment, but with a larger aperture, with a higher cadence, so 10 milliseconds, and also choosing a closer FRB so we can put stringent limits because the FRB will be closer. So the target that we chose was the closest known repeater FRB at the time that we performed the observation. That's FRB 180916, also known as the repeater 3. It's located about 150 megaparsecs away, and it has a well-established period of 16 days approximately. It's also important for this kind of observations to have a well-localized FRB, because the typical field of view of the fast camera imagers are small, so we need to know exactly where to point the optical telescope. So this is the target we chose. Then the camera, I'm going to explain a bit about the instrument we use in the optical. It's called Alopeke. It's in the 8-meter Gemini North telescope in Hawaii. So the design is very compact, it's very simple, and it has two cameras, a blue and a red camera, from which you can choose different filters independently. And there are two main modes, speckle mode and wide field mode. Speckle mode has a very narrow field of view, but so you can resolve, you can reach the close to the diffraction limit in the optical. And the wide field mode, which is the one we're going to use, it has a wider mode, larger pixel size. But here we are not interested in resolving, especially the FRB. We just want to measure any possible flux. So we chose this one based mostly to increase or decrease the cadence, so go to 10 millisecond cadence. For that, we chose the wide field mode with 2x2 binning, pixels twice that size over there, with a region of interest smaller than the 60 arc seconds to also reach a faster readout. So with that setup, we can reach 10 millisecond cadence approximately in the optical. The instrument has a suite of different filters to which we can choose from. And in this particular observations, we chose R filter for the blue camera and the I filter for the red camera. And we have those two observations simultaneously taken. So we coordinated these observations with time because, of course, we wanted to make sure that at the time we were observing in the optical with Gemini North, time was operative. And we also coordinated it to coincide with an active period of the FRB 1809-16, predicted by the 16-day period. And that the observations happened in October 2020, last year. And we were lucky. Well, I'll show you that there was a time pulse at the time of observation, so that's important. Here is the field of view in the optical based on a GMOS Z-band, and the Alopeke field of view is the dashed square. So this is how a single 10 millisecond image look from the Alopeke perspective. And it's important also to have a wide field of view because we have some reference stars that are useful for calibrations. Okay, as I mentioned, there was a pulse observed by time at the time of the Alopeke observations, signal to noise of order of 12, fluence 4.4 Jansky millisecond. And this is the waterfall plot. What I wanted to emphasize here is that the typical pulse, so the pulse of the actual, the width of the pulse detected by time, it's of comparable time span as the cadence we reach in the optical. So that's interesting. So we know, so the experiment, it's as follows. We take several of these images. We register count at the FRB position. We know exactly where to look within the field of view, and we do this in the R filter and the I filter simultaneously. Then we use, for instance, this reference star provide relative astrometry and relative photometry to know to convert counts to flux and to know exactly where to look for within the field of view. So here is results of the observations. So in the y-axis of these plots, we have counts per exposure. Each dot is an individual Alopeke exposure, so one of these images, and at the position of the FRB. And we see that it fluctuates around a mean. The FRB arrival time is given by the shaded region. It has an uncertainty mostly given by the accuracy by the timestamps of the instrument Alopeke, which is about 160 milliseconds. So we know at some time within that range the FRB should have arrived, but we don't know exactly where. So we look at the region. And this is how assuming in the set of exposures look like. As you can see, there is no excess of counts closer or within the expected arrival time in either of the cameras. If we zoom out for all of the observations we took, about 200,000 frames, 100,000 in each camera, we see that there is no excess of counts anywhere close to the FRB coincident with FRB. So from this non-detection of transient optical, we place upper limits based on the counts. Also, yeah, the counts are well behaved in the sense that are following a Gaussian distribution around a mean. We check that, and there are some fluctuations, as you can see, some decrease that and changes as a function of time of the counts. That it's due to weather conditions and systematic about the reading of the instruments, which we can handle very well because we have the reference star that give us a reference to compare with. So here I show you the blue camera counts compared to the reference star counts in the blue camera, scale by 1/6, so we are in the same panel, and we see the same typical fluctuations happening in the star and the FRB position count. So we don't find this to be associated to the extragalactic sky. It's systematic from the atmosphere or of the instrument. Yes.
3 minutes, Nicolas. Sorry.
3 minutes. Okay. Thank you. So the same you can see here in the red camera. So now, so the implications of this. So we place upper limits on this eta parameter, which we follow from Chen et al. 2020. So eta here will be the ratio between the fluences, the integrated fluences in the band, in this case optical and radio. So which goes close to the specific fluences in the optical times the frequency in the optical divided by the frequency in the radio times the specific frequency in the radio. So based on that, we set 3 sigma upper limits for the specific fluences in the optical of about 8 to the 8 times 10 to the minus 4 Jansky millisecond, or 7 depending on the band, which where we compare with the fluence in the time pulse. We can place an eta upper limit of the order of 100. This number needs to be revisited more closely, so that's why we say this is preliminary. Placing this limit in a wider context, here we used a figure adapted from Chen 2020. So the allopeke limits will be here. Here is the y-axis, the eta parameter in different wavelengths as a function of frequency. And our current allopeke limits are constraining compared to other previous experiments done in the optical, and might be interested for ruling out or exploring progenitors of the emission of the FRB pulses. Okay, so let's finish with the summary and conclusions. I have presented high cadence optical high cadence optical observations at the order of 10 milliseconds using Gemini North allopeke instrument on the repeating FRB 180916. Optical observations were coincident with the time FRB pulse at the time. We obtained 100,000 exposures in each filter, R and I filters in the optical, and we didn't see any bright optical emission coincident with the FRB. So we place upper limits based on these non-detections, which imply an eta value in the optical smaller than 100. So this upper limit will disfavor some of the proposed theories of FRB emission mechanisms. Of course, just in the last 30 seconds I have, want to just say that this is only coming from one set of observations, one pulse, so we are not really ruling out etas at this value yet. We want to repeat this, and we have a plan ongoing in the context of the F to the 4th collaboration to repeat this experiment with the same repeater in 2020B, from which, if we are lucky, we might place more stringent limits, especially if we have a brighter FRB pulse coincident with those observations. So stay tuned, and thank you very much for your attention.
Thank you, Nicolas. Thank you for that great talk. All right. So looking at the Q&A here. So first we have a comment by Bing Zhang. Bing writes, just a comment. Z equivalent 17.9 magnitude optical upper limit was placed on the galactic FRB from SGR 1935 during the burst epoch. So this was reported in Lin et al. And if the optical to radio flux ratio of this event is representative, then the chance of detecting fast optical bursts from cosmological FRBs is slim. That's a comment by Bing. If you we can address that, or we can move on to another question that we have by Sergei Popov. So, okay, moving on to the question. So Sergei has a question. What are the limits on the presence of a companion which can produce matter to be irradiated?
The optical limits of a companion, or?
The limits on the presence of a companion.
A companion.
A companion star, I believe that Sergei is thinking of a binary system.
Yeah. Okay, so here these limits are for any optical emission besides what it's in the sky plus galaxy. So if there is any star, it has to be fainter than that limit. I hope that addresses the question.
All right. I see Casey has raised his hand. You can just unmute yourself.
Okay, thanks. Really great result and fortuitous detection. I was curious if there's any sense from the theoretical models for the sources that the optical emission is coherent, and if so, does it point in the same direction as the radio emission?
Do you mean like from theoretical models, if we expect this optical counterpart to be radiating in the same direction as the FRB?
Right, yeah.
Yeah, I don't know. I am not an expert in theoretical models, so I'll defer that answer to the theorists. But I just want to comment broadly that I feel, even though there are very interesting proposed models for explaining the FRB mechanism, we are the floor is open for surprises. So I think we need to be open-minded and perform follow-up at different wavelengths, because that's gonna, when we have a counterpart besides the galactic magnetar, that will be very useful for constraining the mechanism. So,
yeah, I strongly agree with that sentiment. And also, just that we don't know if there's one kind of FRB. So of course, ruling out one
exactly.
doesn't do anything. Yeah.
Great. Casey, just a quick comment from a theorist's perspective. The optical emission in most models that predict optical emission, it's not coherent. So it's incoherent optical emission. And in most models, at least to my knowledge, it would be beamed, either unbeamed or beamed in the direction of the FRB.
Thanks.
All right. Well, if there are no further questions at this time, let's move on to our next talk. Again, you can ask further questions from Nicolas over Slack. So our next speaker is Casey Laha from Caltech. And Casey will be telling us about FRB and PRS populations. And great, take it away, Casey.
Okay, thank you. And I'm sharing now. Does that, oops, you're seeing my notes, aren't you?
No, we're seeing the full screen.
Oh, okay, good. Okay. Okay, thank you. And thank you for the opportunity to speak today. Really great to be here. So I'd like to talk to you about sort of a study or consideration of populations, both on the FRB side, but with a particular focus on these persistent radio sources, so PRS. You'll hear that a lot in this talk. the idea is to try to use PRSs and treat them as sort of a first class, aspect of the FRB population, and thinking about them from that perspective to help us understand the nature of FRBs. So I'll open it with a provocative statement, which was not mine, but there's nothing as useless as a radio source is a sort of famous quote from Jim Condon. And that would be a pretty insulting thing to say if you weren't Jim Condon, because he is a pioneer of measuring radio sources through sky surveys. And the point, of course, is that you measure when you make a measurement in the simplest sense, it's a flux and a position, at some radio frequency. And you might measure something, and then you don't know if that radio source corresponds to a radio star that's in your backyard, sort of a few parsecs away, or a supermassive accreting black hole at the edge of the universe, right? So it's really hard to say physically what's happening just from measuring a radio source. That's Jim's point, and he spent his career certainly thinking about how to make use of them. And the argument I'm making here today is that associations are really when we start to get something of value from measuring radio sources. And we've already heard great presentations in the meeting so far, and we'll hear some more. But spatial associations, if they can be done robustly with a low false association probability, can tell us incredibly, far more information than the radio measurement alone. So environment, tells us the context for the object. So what star formation rate of the host galaxies, is it forming in a globular cluster, and what kind of things live in globular clusters? We've heard about those things. And session 9 will have a lot more on the host galaxy question. Birth event. So if we can tie FRBs, or specifically, any radio source in general to some birth event like a supernova. We heard Charlie talk about that, and that could be a real breakthrough because we know a lot about how, say, a supernova behaves. And so that gives us a lot of contextual information to understand the radio emission. And then third category would be, what comes later, right? So after the birth event, there's some remnant object, whether it be a black hole or a neutron star or some sort of plurionic emission from a nebula, say. And these things, again, we understand them in some broader context, physically what's happening, and then we can interpret the radio emission in an appropriate way. So I'll just make one other note is that, these questions that I'm going to talk about today with persistent radio sources and the population are really important to understand the source question, right? What is the source that makes FRBs, or the sources? But it's also really important to use FRBs as probes, which is one of the sort of long-term goals of the field. If you'd like to use the dispersion measure, scattering, propagation effects to talk about the intergalactic medium, host environments, and so on, we really at some point really need to know very precisely what the environment and the local environment of an FRB is, and how to separate that from propagation effects that are of more relevance to, say, cosmology. So I think the question of associations and understanding the source model has short-term value and long-term value. So when we talk about persistent radio sources, so the radio source that's associated with a fast radio burst, we have a name for that, we call it a PRS. It's, again, it has incredible value once we identified it as being associated with FRB, because we know FRBs are an incredible mystery, and now we have this peculiar radio emission that's persistent, that is located within, say, a parsec or so of this source of these luminous bursts. And so the archetype of this combination FRB PRS source is FRB2011-02, which by coincidence was the first one localized. It turned out to be extremely valuable for understanding and modeling the nature of the environment of that FRB. Subsequent observations found that it was extremely magnetized plasma that was associated with the environment of the FRB, and we can characterize the spectrum and do modeling of that. There's still ongoing work with time evolution of the PRS and all sorts of great stuff we can do. That constrains things like the energy, the age of the environments that's formed the FRB. So there's just really a lot that came out of this one identification of just a radio source, right? As this uninteresting thing, because it's associated with the FRB. Now, those were the sort of the heady days, because it seemed so peculiar that we thought, in fact, there's a nice paper by Terne Eftekhari, who talked about what would happen if we had 10 more localizations. You know, if they looked like this in terms of their host galaxy, in terms of their association with persistent radio sources, perhaps you would have solved the origin question for FRBs, you know, within a few years. Now, in fact, we know today it's, you know, we've done more of those localizations. We have more information, and if anything, the question is diverged, right? We have not converged. We have a more diversity of hosts, and there's a very, there is not in the subsequent, say, 20 localizations or so of FRBs, and ones with good associations with host galaxies and environments, deep radio imaging. We have a diversity of contexts and, you know, associations. So this is just a kind of a highly biased sample of sort of VLA localizations. The top row shows the VLA image. The middle shows the VLA deep image, usually from commensal data at the same time. And the bottom row shows optical follow-up, showing host galaxy and other environment of the FRB. Right, so diversity of hosts and associations. But one exciting thing that's come out recently is, was hinted by Reshma Anna Thomas in her polarimetry talk on the first day, which is FRB 190520. We'll hear more about it from Dee Lee in a breaking news talk, I hope, at the end of the conference. And I won't go into in great detail other than to say that it is remarkably similar to FRB 121102. And so you can see that we have a localization, we have a persistent radio source, which we can say with great confidence is a compact, co-located persistent radio source with the FRB. And then we have a relatively, you know, diminutive sort of host galaxy. And so in many ways, we consider 190520 to be a clone of 121102. So that raises a whole host of questions. I think, first of all, it sort of elevates the question of PRS again. It makes it relevant to revisit and think about that 121102 in the broader context, and really treat the PRS as, you know, a fundamental aspect of the lives of at least some kinds of FRBs, right? So some of them have this association, and it's pretty important and informative to understanding the origin question. So that's the context for what I wanted to talk about today. So the rest of my talk, I'm going to go through our sort of study of archival data and collating results from papers and sky surveys to try to constrain and talk about correlations between properties of PRSs and FRBs and what that means for the population. So the motivating questions are, you know, how common are PRSs and FRBs? So we used to sort of think that it was a pretty rare thing, but now we have two examples. So we're going to dive into a bit of that question. What is the fraction of FRBs that have PRS emission? Two, how are FRB and PRS properties correlated? So that's another interesting thing to talk about. Tells us something about why we have PRS emission, potentially. And third, can we find PRSs without FRBs? You know, PRSs are luminous radio sources. Maybe we can turn the problem around and start to look for PRSs instead of FRBs. So to do this in a meaningful way, I think we need to step back a bit and think about what we mean when we say FRB and PRS. So you know, we have a good sample of localizations, and so we can start to say things and discuss things in sort of physical units rather than observationally convenient things, which are, say, fluences. And so there's always a bit of a choice, a balance between, you know, when you define what FRB means and what PRS means, you have to balance between what measurements exist and what's convenient and what's useful. I will propose some definitions, and people are free to choose different ones, but I find these to be useful. So my definition for the purposes of today is that a FRB is a radio transient with a luminosity, particular luminosity of 10 to the 29 ergs per hertz, greater than 10 to the 29 ergs per hertz, and a timescale which is much faster than a second, presumably, you know, being inclusive of the microsecond, nanosecond scales that we've heard discussed here. The point is that it's a coherent process that is extremely energetic and detectable at cosmological distances. Repeater in that context is just more than one, right? We get more than one from the same source, then we call it a repeater. And then third, this one's maybe the most open to interpretation and discussion, but I'm going to argue that a persistent radioluminosity of 10 to the 29 ergs per second per hertz is an appropriate definition for a PRS if that source is directly associated with an FRB. And when I say directly, I mean we can just clearly say that it's not related to, say, star formation in the host galaxy, and that it is spatially coincident with the FRB. That's very clearly been shown for 121102, and I think we will ultimately show that well for 1905-20. So just some quick notes based on those definitions. Maybe this is where people get sensitive to it. we can discuss in Slack. STR 1935 is an FRB, but not a repeater. That's just how it turns out. I'm open to discussion. And FRB 2011-24A has no PRS because it has persistent radio emission in the host galaxy, but not a PRS. So when if you take these definitions, then you can consider where the PRSs are and where we know there are no PRSs according to that definition. And so this is a plot that shows radioluminosity detections and limits for the sample of localized FRBs, right? So we know roughly where the distance is for these, and we know limits on the radio brightness associated with them, so we can put limits in those cases. And some of these are limits from, say, sky surveys, like the VLA Sky Survey, or RACS from ASCAP. And what's surprising is that in many cases, we don't have very good limits, in fact. So that horizontal line shows the 10 to the 29 value, and 2 points with circles and stars show the detections, and all the other points show upper limits. So the points that are below that line that are upper limits are formally called, have no PRS association. The labeled points are actually repeaters. That's another thing I should say. So some repeaters have good limits, some don't. Some non-repeaters have good limits and some don't. And so we can sort of categorize things. And I thought it was appropriate to use sort of a Venn diagram. I'm not going to fill it in because I just want to sort of lay it out here, but I'll fill it in a second. So, there's a great big circle outside of this, which is all FRBs, and there's a subset of those which we know to be repeating, and there's a subset of all FRBs which we know to be localized well. Those tend to overlap a little bit. There's this LPRS circle, which is that subset of localized FRBs which are have meaningfully constrained PRS emission. It's also smaller than the number that's localized. And then there's finally the smallest circle shows the detections, the number of PRSs measured. And so if you fill in the numbers, it looks something like this. The numbers might change a little bit depending on your definition or how you count limits. But broadly speaking, we have about 20 to 25 localized FRBs. Most of them are non-repeaters, and then there are about 5 localized repeaters. Some of this I should say is as work in prep and will be submitted in the next week or so. So I apologize for that. And so 2 of the repeating FRBs are localized and have PRS emission. 8 of the localized, yes.
Oh, sorry, just 2 minutes. My apologies.
Okay. So eight of the FRBs are localized with non-repeaters. And so broadly, the answer to the first question I raised is you can just sort of, if you take this as an unbiased sample, it's the ones that we were able to observe, 15% of FRBs have a persistent radio source. And here's some names if that's helpful. I'll give you some sense of what we're talking about. So the second question is, are there correlations between FRB properties and PRS properties? So you'll note that 2 of the 5 repeaters have PRSs. You can estimate the true probability, the true distribution of PRS fraction as a function of we'll see. So if you treat it as a coin flip, biased coin flip problem, is a binomial distribution with a true PRS fraction, then the measurement of 2 of 5 gives you a constraint on the probability of that true fraction. And so you can do this for the repeater and non-repeater fraction. And in fact, it looks like there is sort of some evidence that PRSs prefer to be with repeaters. There are potentially some biases in how that sample is defined, and that's certainly worth scrutinizing carefully. But I think we have some weak evidence potentially that there is a distinction between where PRSs like to live, which correlates with FRB activity. in repetition. I'll skip this slide for interest of time, but there's potentially evidence, that some FRBs have very high anomalous local DM, and that may also be a prediction, suggest that some sources might have a persistent radio source associated with them, which would be consistent with some models of how FRBs form and what their environment is like. And then final point, which I'll try to squeeze in, is finding PRSs without FRBs. So we have a pretty good idea of what the FRB all-sky rate is. So it's actually pretty comparable to the core collapse supernova rate, which is a fun fact, 10 to the 5 per cubic gigaparsec per year. You can then, if you have an estimate of the mean repetition rate per FRB and an estimate of the beaming fraction, so how many of them are beamed in our direction, you can actually back out the true source density, right, in terms of sources per gigaparsec. And so Liam Connor is a collaborator on this. He had some nice ideas for using the CHIME catalog release to sort of bound the repetition rate, sort of assuming that either all FRBs are repeaters with some power law distribution of repetition rates, or that there's truly non-repeating and repeating events, and then taking a mean of those two populations and calculate a gross repetition rate. And so with those bounds in the rate, we can then back out, with an assumed beaming fraction, we can back out the true source density. And it's a pretty wide range, but that number is it's a physical density of sources in the sky, right, in the local universe. So that's, to my knowledge, that might be one of the first constraints on that density of sources of FRBs. And then one more leap, which is that we can take this fraction of sources of FRBs with PRSs, and we can then calculate the density of PRSs in the sky. And so if you push that through, you can get an estimate of how many sources there are within some volume of sky that you were sensitive to, say with a sky survey. And there's something like potentially thousands of PRSs that are in this VLA sky survey. So when you look at these flux density distributions, like say when people on the left panel, bottom panel, there's this distribution of flux density used for cosmology and other applications. There's bright sources tend to be attributed to AGN. The fainter sources correspond to, say, star formation activity. And those are like the two main categories of sources that you see in the extragalactic radio sky. And what I'm arguing here is that there's probably, maybe a few percent of those sources which are in fact something that could be totally different, right? It could be a PRS driven by some really, new phenomenon. And so that's something I'm pretty excited about exploring and finding independent of the FRB question. And I'll just note that these PRSs are often offset from their nuclei, and so they are distinguishable from AGN, which is the dominant population. So I think it's an exciting potential exploration for sky surveys in combination with FRB science. So I will close with this slide, and I'm at the end of my time, so I will stop and take questions here. Thanks.
Thank you, Casey. Really, really interesting and amazing new stuff. So we only have time for maybe one brief question, perhaps two. So I'll start with the chat. Mohit asks, Casey, fascinating stuff. Did you estimate the chance coincidence probability of finding two FRBs with PSR out of a sample of at least 7, where radio observations are sensitive enough to detect 121102-like sources?
So that so the question is, if you have deep radio images, are you likely to find a chance coincidence of a radio source with the FRB? I think I interpret that correctly. And that analysis was, we're taking the analysis that was in, initial publications. I think for the most part, the density of background radio sources in the sky is quite low. And so with ARC-SEC and localization, you can rule out chance coincidence pretty well. Tends to be the chance association probability is lower than the galaxy chance association probability. So we're not too worried about that effect.
Great, thanks. Jason also has a question or a comment in your PRS upper limit plot. I guess 180916D should have been 180916B.
Oh.
I can't keep track of those telephone numbers.
Yeah, sorry. Yeah, I will fix that. Thank you, Jason.
Excellent. Well, this is really fascinating stuff, and I'm sure there'll be many more questions on Slack, but let's thank Casey for now and move on to our next speaker. All right, so our next talk is a pre-recorded talk. We'll hear from Jielai Zhang from Swinburne University, who will tell us about simultaneous multi-wavelength observations of 2 FRBs. If anyone from her team is on the call, please do Slack me or let me know so we can point questions towards you. Otherwise, you can write questions in the Slack and I'm sure they'll answer later.
Can you see that, Ben? Are you seeing the...
I can see not in full screen.
Okay, let's see if this... It's having problems picking up this window. One sec. Ah, there we go.
Looks good. I'm not getting any audio, Jason.
Thank you to the conference organizers for having me speak at this conference, FRB 2021. Despite it being on Zoom, I'm online. I'm delighted to be here to talk to you today about 2 FRBs detected during the Deeper, Wider, Faster program. The first part of my talk will be an introduction, super fast, since this is an FRB conference. And the second part will be to tell you what the Deeper, Wider, Faster program is, followed by what we did and what we found in September 2020. As you all know, FRBs have been found at radio wavelength, but FRB counterparts in other parts of the EM spectrum have not been found. And this is not from lack of trying. Many studies have tried lots of different techniques, including not searching coincident in time, but just any spatial association. There's been no FRB counterparts found so far. And here I've got a bunch of studies, but it's not exhaustive. So if you see one that you really like that's not on here, feel free to shout it out to me. The closest thing to an FRB counterpart detected so far was 2 FRB-like bursts from a galactic magnetar. So these 2 bursts were not as bright as the extragalactic population of FRBs, but they were preceded by 2 consecutive X-ray bursts 8.6 seconds beforehand. This confirmed that magnetars, which this X-ray source is a magnetar, can give FRB-like bursts. And this amazing discovery shows how important it is to be on the field at the same time with multiple wavelengths to catch this coherent emission, and it can make really exciting discoveries. So that's what the Deeper, Wider, Faster program is all about. Before I tell you in detail what it is, let me introduce you to the team. The PI is Jeff Cookie at Swinburne. We've got 2 PhD students, Sarah Webb and Simon Good, 2 postdocs, plus me, 3 postdocs, Dugu Dobi and A. Smaller, and previous members include Igor and Tyler. The Deeper, Wider, Faster program coordinates observations with multi-wavelength telescopes to do simultaneous observing of the same field of view. And we do this not only to study fast radio bursts, but also other fast sub-second to hour timescale transients, such as supernova shock breakout, kilonovae, flare stars, gamma ray bursts, to name a few. Transients that have timescales of seconds or that are very short cannot use a follow-up strategy to catch coherent emission, because there's just not enough time to trigger follow-up observations. For the Deeper, Wider, Faster program, we coordinate telescopes across the whole wavelength range to do simultaneous observing. In the radio, that includes the Parkes Radio Telescope or Murray-Yang, but we've also used ASCAP and Meerkat. In the microwave, the South Pole Telescope. Our weak link is infrared, but exciting infrared telescopes are coming online in the future, so hopefully this gap will be filled. In the visible, the telescope we use most is the 4-meter at CTIO using the DE-CAM instrument. And in ultraviolet, the AstroSat Indian Space Telescope, which also actually observes in X-ray. In X-ray, we've got the Chinese telescope, HXMT Insight, and in gamma ray, SWIFT, in particular, the Burst Alert Telescope. So the Deeper, Wider, Faster program coordinates all these telescopes around the globe as well as in space to simultaneously observe the same part of the sky before any event has even gone off, but also during any transient events, little lightning, as well as after. Such a simultaneous continuous observing campaign is very different to follow-up observations. And it's important to do something like this to catch coherent emission, because X-rays, as we see, can arrive tens of seconds before the radio signal if it's emitted coherently. Of course, associated bursts in any other wavelength can arrive an unknown amount of time before or after the FRB radio signal. Since we just stare and wait for exciting events, it's very important to maximize the volume probed by our telescopes. So we use the largest aperture telescopes with the largest fields of view. Often it is a trade-off, but we've got these are some examples of telescopes that we use with very well-matched fields of view. The scale here bar shows 1 degree, and in the background is our main optical telescope, CTIO. The Parkes telescope, you can see, is very well matched, as well as this multi-fiber, multi-object spectrograph, AAT. The long glow is shown here, and the South Pole telescope. Many of our telescopes have larger fields of view than this, such as SWIFT, HXMT, AstroSat, ASCAP, PR-Auger. So that's what the deeper and the wider part of deeper, wider, faster is. Deeper, larger apertures, and wider, larger fields of view. Since we stare and wait, field selection is extremely important. So one of the main things we like to do is target FRB repeaters to increase the chances of finding an FRB. But another important thing is the ability to do simultaneous observing. And this is actually logistically and coordinatingly very difficult to coordinate. So I would like to advertise some useful work done by an internship student of mine, Andrews Menyo. He worked with me over Zoom. We didn't see each other in person at all for about 2.5 months. And he's from Northwestern University in South Africa doing a master's. So he wrote a piece of code where you can enter the details of any 2 telescopes, as well as the period of time that you want to co-observe with those 2 telescopes. And he's able to plot the total amount of co-observability time with those 2 telescopes for any RI and DEC. So this is an example of, I believe, ASCAP and the CTIO telescope. And so we actually use this to plan DWF observing runs, at least, yeah, so it's very useful. So deeper, wider, we got that covered. What is faster? You probably guessed that it's about faster cadence or fast transients, but it also is for fast discovery and data processing in order to do fast follow-up observations. I've already talked a lot about one part of the deeper, wider, faster program, but there's actually 4 parts. The part I've talked a lot about is the coordinated, simultaneous multi-messenger observations. So that's done. The second part is we do real-time data processing and transient detection within minutes, so that this can then trigger rapid response and conventional target of opportunity observations. This is done hours to next day, and this is done using telescopes that partner with the DWF program, as well as through a whole bunch of proposals that we write throughout the year. The fourth part of DWF is long-term follow-up observations over weeks. So this is to look at the long-term evolution of any slower evolving transients, as well as to follow up on host galaxy properties of extragalactic transients. Now that you know a bit about deeper, wider, faster, and how we attempt to find FRB counterparts, let me tell you about our September observing run. Before I go into detail, I'd like to advertise some students that helped with the run. Vivek Gupta, who you heard from earlier in the conference. Sarah Caddy is a PhD student at Macquarie University. Junho Kim, Seoul National University, and Jong-Mook Kim is about to start his PhD. In September 2020, we had 6 half nights of simultaneous multi-wavelength observations. So this is about 5.5 to 6 hours each night. We targeted 2 fields that we observed every single night in the southern hemisphere. This plot is an extinction map, and you can see the Milky Way galaxy as well as the large and small Magellanic Clouds. We did not detect any FRBs in this field, so I will focus on this field. This is centered on FRB 190711, which is the localized and repeating FRB. And we observed this field for about 2 to 2.5 hours every night over 6 nights. This is a plot showing all the observations that we did. On the x-axis is time, and on the y-axis is all the different telescopes that we used. The blue colors are the high energy telescopes, green, the visible wavelength telescopes, and in red are our radio telescopes. The 2 black lines indicate the times at which we detected our 2 FRB signals. And so let me tell you, actually, before I do that, in our optical telescopes, our main optical telescope was KMT-NET, which is a 1.6 meter Korean telescope situated in Australia. We had time on the CTIO 4 meter telescope, but unfortunately due to COVID, it was offline. So the 2 FRBs that we detected on the first and last day were not from the repeater 190711, which is situated here. This is a KMT-NET image of the field, which is 2 by 2 degrees. This repeating FRB has a DM of about 600. The first FRB on the first day had a signal to noise about 10, and it was detected here. It had almost 500 DM, which is comparable to this FRB. The second FRB we detected was very high signal to noise. You can even see it in this image here with a D. Oh, this is wrong. This should be 560. But the redshift is correct. The redshift upper limit is correct. Sorry about that, everyone. So yeah, this FRB was very high signal to noise. So one thing that's interesting is that we have 3 FRBs in this very small field. This yellow circle here is a 40 arc-minute radius around the repeater. So something that we're going to look into if there's a cluster environment in this region. Of interest is that the signal to noise 100 FRB, in that beam, we also detected a low signal to noise 7 signal, FRB like signal 3 days beforehand, but it was likely noise. And also it's in the region is an unclassified optical transient that had 1 detection in a clear filter about a year beforehand. It dropped 0.7 mags in a clear filter over 4 minutes, which is really crazy, but no other observations of this was found. So I can only leave it at that. But it's just very interesting because 3 things happen in the same region. At this point, I can reveal we found no FRB counterparts and only have upper limits. Upper limits set is also not complete because observing conditions are not always in our control. So let me tell you a little bit about that. At the time of the first FRB, HXMT was over the South Atlantic anomaly. And that just means the data is completely useless. Our optical telescopes, ZADCO was not operating. Huntsman and Panoptix, the field of view didn't cover the FRB location. KMT-NET, beautiful, covered the location, but it broke for 6 minutes, exactly at the time of the FRB. What are you going to do? For the FRB on the last night of observing, all the optical were clouded out. However, we did get HXMT and AstroSat data. For a SWIFT, we actually don't point SWIFT. However, because the SWIFT burst alert telescope has a really large field of view, there's a good chance that it overlaps with where you want to look. So what we can do is trigger a data dump, which normally does not get saved if there's no BERT alert. But we can trigger a data dump to search for anything afterwards, anything low signature noise. However, unfortunately, it wasn't observing on our field at the time. This is the plot showing all the upper limits that we derived using our data. Starting this line is the Monday, is the FRB on the first day, and this is FRB on the second day. We have no coincident observations despite coordinating so many telescopes for the first FRB. However, other than the 6-minute dropout of our optical telescope, we do have upper limits for all around the FRB except for 6 minutes on the FRB. This allowed us to derive fluence ratio lower limits of about 10⁻⁻11. We didn't find any transients in our optical data. There were some time variable sources, but they were stars. For this particular FRB, we were able to derive X-ray, radio to X-ray fluence ratios, and that's our number there. We were able to do a whole host of follow-up observations on the field, including monitoring FRBs with Meerkat on the last row here, as well as Huntsman, KMT-net, Mirror Lake, Master, and Hess, to name a few, but there were no repeat bursts that were found. DWF has been awarded CTIO, our main optical telescope, time for the next 3 years. And this goes deeper than what we used here for KMT-net, even with a shorter exposure time. New infrared telescopes, as I said at the beginning of the talk, are coming online, and that we've been discussing collaborations with them, including the Prime Telescope in South Africa and the Nancy Grace Roman Telescope and DREAMS. Our collaborators continue to be willing to contribute to the future observing runs. And very excitingly, Huntsman may join DWF runs with ultra-fast exposures using CMOS cameras. So the future is bright to explore the fast, faint parameter space of FRB multi-wavelength counterparts before, during, and after FRB radio emission with the Deeper, Wider, Faster program. Thank you very much.
All right. Thank you for that and very interesting talk. Please post questions for Jielai on Slack, and I'm sure she'll be happy to answer at a later point. I guess it's the middle of the night for her in Australia. So with that, let's move on to our next talk. Our next speaker is Sibasish Laha from NASA and University of Maryland. And he will tell us about the simultaneous fast NICER campaigns observing FRB2011-02 and important constraints on the FRB mechanism. So take it away.
Thanks very much, Ben. I'll just share my slide. Can you see my slide?
Yes, I can see it now in full screen.
Perfect. So thanks very much to the conference organizers to give me the opportunity to talk. I am Sibasish, and I am a Swift mission scientist at NASA Goddard Space Flight Center. And this work is based on multi-institution, multi-wavelength collaborations throughout the world. And a special thanks to the FAST team, the NICER team, and the Swift teams for their support and help for during the analysis. And I must mention that this is an ongoing work, so it's the results are the final results are still being worked up. So I'll talk on about FRB180301, where we have the NICER and fast simultaneous observations, and also FRB180916 using Swift BAT observations. So the last year's paper by Luo et al. Using fast observations found that the polarization angle changes have been detected for 180301, which implies a magnetospheric origin with more efficient radio emission from a magnetar, if it is a magnetar which is creating the FRB. And for FRB2011-02, there hasn't been detections of any polarization angle changes, which may suggest that relativistic shock models are the reason for the emissions. So this prompted us to observe these two sources simultaneously with a fast telescope in radio, with a NICER, which is soft X-ray instrument on board the International Space Station, simultaneously in these two wavelength bands. So FAST, as we all know that it's the largest single-dish radio telescope and very highly sensitive for FRBs which are very far away. For example, these two sources are technically around 1 gigaparsec away from us. And we report only the FRB 180301 in this talk, as FRB 121102 work is still underway. And hopefully in the next few weeks, you will see the publication in the archive about these sources. So about the source 180301, it is around a gigaparsec away, and it's repeating, but apparently not periodic. It has a high degree of linear polarization, similar to 121102, but it shows polarization angle swings. And the previous detections from this source has shown the peak radio flux densities range from around 5.3 to 94.1 millijanskis. And the burst rate is around 1.2 per hour during the bursting period. And its extremely high brightness requires coherent radiation models. We conducted simultaneous observations of FAST and NICER. It happened on 4th, 9th, and 19th of March. FAST detected 6 bright bursts during these observations, and 4 of which happened to occur during the NICER observations. And the radio burst peak flux densities ranged from around 28 to 96 millijanskis. And the burst widths, time widths ranged around 1 to 5.52 milliseconds. And the burst fluences were around 27 to 170 milliseconds. And all the bursts were above 10 sigma, signal to noise. So NICER is a very unique instrument. The full form is Neutron Star Interior Composition Explorer. It is on board the International Space Station, and it is a non-imaging X-ray telescope, which means that it's just a photon bucket, and it has a very high effective area. And the most important criteria it has is the microsecond time resolution, and which is very, very important in constraining the neutron star equation state and other properties. So, and it operates in the 0.2 to 12 keV, and it's very unique to study the FRBs in the sense that FRBs happen in millisecond timescales, and this gives us a unique opportunity. Unlike, for example, Chandra does not have this timed resolution, for example. But the downside of a non-imaging X-ray telescope is that the background is not determined well, in the sense that unlike Chandra or XMM, where we have imaging telescopes, we have the background well determined. Even a few photon counts from Chandra is a detection. In NICER, it's not imaging, so we have to model the background. We have to estimate the background from known background sources and background events that can happen due to high energy particles striking the detectors. So the NICER observations and data reprocessing were done with standard steps, and also we have taken extra cautious steps regarding the elevation angle, the bright earth limb, so that no extra spurious counts happen in our events. And also we have taken steps to filter out the South Atlantic anomaly, which the telescope, actually the ISS, goes through the SAA quite a few times a day. And these are regions of high energy particles, and they give you huge number of counts in the detector, which are not or not actual source photon counts. So so we filtered very carefully, but still we detected wings. I'll show you the light curves. We still detected wings in the light curve due to improper SA filtering, and we have to be careful about chopping off the data. And the radio bursts happened, 2 of them happened during the wings. So if we include the wings, the net count rate is kind of slightly larger. It's 1.2 counts per second. And if we get rid of the wings, it's around 0.69 counts per second, which is standard NISO background counts. And we used this standard background counts for upper limits. And the spoiler is that we don't detect any X-ray counterpart during these observations. So, and the NISO background background has been used, determined using both the models provided by the NISO team. One of them is the NISO background estimator, and another one is the NISO BACGEN 3C50. So we have done both ways when we saw that our data is background dominated. So this is NISO observation 1, which is a few hundreds of seconds. Around 700 seconds. There is no FRB during this observation. But in the second run of the observation, is the 9th of March, we find 3 bursts during, 2 bursts happened during the NISO observations, and one of them falling in between when it was within the SAA. And all of the radio times are de-dispersed arrival time at infinite frequency. And we have matched this with the NJD-TDB. So that we are observing the right time from the radio and the X-rays. And the last run for NISO happened on 19th of March this year. And fortunately, 2 bursts happened, bright bursts happened as detected by FAST during the NISO observation. The radio time is dispersed again. And you see that the wings that are coming up is because of the SAA, the South Atlantic anomaly, and we have to get rid of that while estimating the right background. So I'll give an example of like how the background spectra, the time integrated background spectra would look like. It's around few kiloseconds background spectrum. So this is the source plus background, and the top one is the calculated background spectrum. So we see that the background spectrum is actually dominating. The modeled background is more than, the predicted background is more than actual source plus background that we observe. So it's completely background dominated. And we don't detect any source counts. That's what we mentioned, at least, in a time averaged way. And NISO is the only X-ray telescope with such a large effective area and with a millisecond microsecond time resolution, I should say. So I have binned it in millisecond bins per millisecond, and you can see that it's kind of, the background shows off clearly that it's background, and there is not much of emission during the FRB bursts. So these are radio burst 5 and 6. We don't see any excess emission above the background. And we are actually currently looking into, we are currently working into putting strict upper limits on the Poisson and non-Poissonian fluctuations around the detection times. That will give us a very strong upper limit on these X-ray photon counts. And for example, if you zoom into like the actual millisecond time bin around radio burst 5, and this burst actually happened over a time period of like 2.5 milliseconds, we see that the count rate is consistent with 0. At least there is no excess emission which is apparent above the background. And so we don't, technically we don't detect anything, but we are in the process of simulating the upper limit using the Poisson fluctuations, and we will quote some values in the next few weeks. But to give you a handle on what exactly we have measured is we have X-ray flux upper limits on the persistent flux, which is around integrated over 2 kiloseconds, is around 7.5 10⁻12, which gives us an upper limit of the luminosity, 8.48 1044. Assuming no intrinsic absorption, of course. And if there is an absorption intrinsic to the source itself, then the luminosity will go up. And the typical radio fluence, for example, for burst 5 is around 1 E-19. And typical eta, I mean, which we are still calculating, would be the lower limit on eta would be around 10⁻8. So we are still calculating this, so I have not quoted this. And that's kind of consistent with the other studies in X-rays. And if an SGR 1935 type event happened at 1 gigaparsec, definitely NICER would not be able to detect such an event happening at that distance. I mean, the expected X-ray fluence would be of the order of 10⁻14, which is much lower than, lower than what NICER can detect. So the next thing we want to...
Sorry, 3 minutes.
Okay, next thing we want to ask is, can we rule out magnetar giant flares? Technically, yes, in some sense, because typically considering 1806 type flares up to 1047 arcs per second, if we put it at 1 gigaparsecs, we would expect a flux of 8.8 E-10, which is technically detectable by NICER, but we don't detect any. In line with the polarization angle measurements of Luo et al., we think the magnetospheric origin is more favored for this FRB, where the radio efficiency can be much higher than the X-ray emission efficiency. I'll just briefly mention about the Swift BAT view of 180916. I think Aaron will talk more about Swift BAT event files, data files for FRBs. What I'll talk here about is 180916, FRB 180916, which is at one of the most nearby FRBs at 140 megaparsec, has a period of 16.35 days and a burst rate of 2. And this is a very interesting source because Swift actually, the burst telescope surveys the sky most of the time whenever it's looking at other sources. And this survey data is very crucial because it has a very nice localization, and you have a 300-second integrated time spectra from these data sets. And these are all available in HISARC. And this BAT is one of the only among the few hard X-ray telescopes currently working. And this is a very crucial energy band for galactic, giant magnetar flares. And for example, like the flares from SGR 1935 and 1806 has been detected by BAT, but these are all galactic magnetars. I'm talking about extragalactic sources. But even then, it's worthwhile looking at the BAT observations. So the motivations is, during the burst storms, the magnetar persistent X-ray emission flux can increase by orders of magnitude, and it may take months to years to recover the pre-outburst levels. And the second motivation would be the magnetar giant flares consisting of like 1047 arcs per second spike, followed by softer pulsating tail, can last up to several minutes. And these are all very interesting emission in X-rays, and hard X-rays, I should say, which could be detected by Swift BAT. And we have analyzed around 250 such observations. All are like integrated over 300 seconds or more. And so typical spectrum would look like this. And I should say that BAT is a very unique instrument in the sense that it's a coded mask imaging, where you have the spectrum, the background is well estimated, and it gets, you can subtract very easily. And this is a background subtracted spectrum, and you don't have to deal with the background. And we don't see any signal above the background. That's what we find And for all of these observations, we have done this spectral analysis, and we have used the background variance, the 5 times the background variance, to estimate the 5 sigma upper limit on this flux. And the typical 5 sigma upper limit is 7e minus 10 over integration time. So, this is not as strong constraints as obtained from Chandra, but these are definitely consistent with those obtained by other instruments. And the conclusions are, we can possibly rule out energetic giant flares, which dominate around like few hundred seconds, and a luminosity of 44 to 47 seconds, and the pulsating tails. And we can also rule out any persistent emission with that upper limit of the luminosity. And these disfavor shock models that are more efficient for X-ray emission, and favors magnetospheric radio emission from like odomagnetars for this FRB. And to mention, like, these are consistent with previous works with other X-ray instruments by Scholz, Perlman, Tavani, Pilia, and other authors on this source. Thank you very much, and stay tuned for more results on these FRBs with NICER and SwiftBAT. Thank you.
Thank you very much. All right, that was very interesting. So people are welcome to type in questions in the Q&A. While we're waiting for questions, I'll ask one. So how much deeper can you go by repeated observation, stacking, waiting, basically staring at the source and stacking up observations where you know that FRBs were emitted? So within, I don't know, 10 millisecond time windows from detection of FRB, but many of such cases.
I mean, you're talking of NICER, right? So yeah, NICER, yeah, we can go quite below, like it's around 10. I mean, I don't have a number right offhand right now, but it's quite constraining, like 10 minus 13 flux, or like not as good as Chandra. Chandra is time integrated, but very high effective area, but NICER can go quite good. So constraining the eta, I think we can constrain eta quite well, given the fact that we have millisecond order time bin. Yeah.
Thank you. All right. Any other questions on the Q&A or Slack? I'll wait for another minute or two. Yeah, I guess maybe another question then in the meantime, I'll just keep asking. You mentioned that you think that these constraints constrain the shock models more than the magnetospheric models, and I was just curious, yeah, as to why. I think the values for eta that you were getting were, very interesting, but still nowhere near the kind of predictions from both models. So yes. I wonder how we can constrain them better.
So the only way is to have better instruments and more effective area with high time resolution, or else like the recent results by Bharadwaj that we have nearer FRBs, and we follow up the nearer FRBs which are like few megaparsecs away. Yeah, that's the only way that we can. I mean, more observations of these FRBs would help us.
Great, thanks. Yeah, I'm all in favor for discovering more nearby FRBs.
Thank you.
All right. Well, I think we have to move on to our final speaker for the session. So our final talk will be by Aaron Tohuvavohu from University of Toronto, and he'll tell us about digging for high energy FRB counterparts in the BAT. So take it away, Aaron.
Can you hear me?
Yep.
Okay, and you can see the slides.
Yep, and yep, now in full screen.
Thank you. Yeah, okay. So thank you very much. My name is Aaron Tohuvavohu. I'm a PhD student at the University of Toronto. I'm going to be talking about searching for high energy counterparts to fast radio bursts, both prompt emission in hard X-rays and gamma rays, and also afterglow like emission on the order of tens of minutes after the burst in X-ray and UV. And this work has been done with a bunch of people, some of whom are shown on the screen. Jimmy Delaney is a new postdoc at Alabama. He just got his PhD at Penn State, and he's done a lot of the work I'll be talking about here on the statistics and search techniques that we are, brand new ways of analyzing BAT data. Jamie Kenna at Penn State, we built the whole operations chain for this, and Casey Law and the BLA RealFast team and Andrew Zwanigo with the Chime FRB team provide our triggers and did a lot of work getting us the triggers that are so critical. So I have to thank Charlie and the other previous speakers in this session for hopefully motivating why you would care about multi-wavelength searches for FRB counterparts. I'm not gonna really try and motivate it that hard because they did a great job. But what I will say is that there is a reason why we want not only to look for multi-wavelength counterparts, but particularly in the GRB or SGR or X-ray flare, or whatever you want to call it regime. And there's various reasons. Many cataclysmic progenitor scenarios predict high energy counterparts, whether they're prompt counterparts or afterglows. And the only EM counterpart of a putative FRB to date was an X-ray flare or a GRB. And this is very important, and it motivates, I think, searching for more of these. But in particular, we cannot just depend on the searches that are currently running in order to find these, and that's because they're faint. SGR 1935 flare would not be detectable by conventional means beyond about 25 kiloparsecs. That's the X-ray flare coincident with the FRB 200428. Even magnetar giant flares are very difficult to detect extragalactically. They're bright, but most detectors won't see them beyond about 10 megaparsecs. And then what we found from the joint work with gravitational waves and GRBs is that while classically we detect these cosmological GRBs with EISOs of something like 10 to the 51 ergs, the local population of GRBs, which are much more likely because of selection to be off axis, are substantially fainter by maybe 4 orders of magnitude. So GRB 170817 isn't detectable classically beyond 50 megaparsecs without targeted searches. So this is hopefully motivating why we want to, 1, look in the X-ray and gamma ray regime, and 2, do sensitive targeted searches. And I'm going to argue that SWIFT is the best instrument to do this with. SWIFT is a space observatory for people who aren't familiar. It has 3 instruments on board. There's the Burst Alert Telescope, the BAT, which we've heard mentioned by Jielai, and then Sibasish was talking about it just a moment ago. It has a 7,000 square degree field of view and is the highest effective area GRB mission and most sensitive GRB mission in current operation, and also crucially the only one that regularly localizes GRBs to arc-minute precision. And then also on board SWIFT are 2 pointed narrow field of view telescopes, the X-ray telescope and the optical telescope. And I'm going to be talking about using all of these instruments today, but focusing on the BAT. So the BAT, as Sibasish referenced, is a sort of unique instrument. It's a coded aperture telescope, so gamma rays cannot be focused. And if you want to get localization, one of the only ways to do this is to basically use the dark arcs and code your detector plane via a shadowgram. So the detector plane is about a half a square meter, and then 1 meter above it, there's a coded aperture mask, which is 50,000 holes. Half of them are filled with lead, and half of them are empty. And if a gamma ray source shines on the mask, it casts a shadow onto the detector. And if you arrange the lead tiles in your mask in a smart way, you can break all of the shadow degeneracies and uniquely encode different shadows for any possible arrangement of gamma ray sources on the sky. And then you take your observed shadowgram and you deconvolve it or cross-correlate it with your mask, normally by a fast Fourier transform, and reconstruct a sky image. And this is the way that coded aperture imaging has been done for the past 40 years, and for the past 17 years since SWIFT launched, and it's been very successful. As I mentioned, the SWIFT Burst Alert Telescope is the most sensitive GRB detector in operation, and intrinsically can detect GRBs farther than any other facility, or X-ray flares or SGRs or whatever you want. With the event data, the time tag event data, so this is each count detected by the detector, tagged with 100 microsecond resolution timing, an energy, and a spatial location on the detector, you can perform really sensitive GRB searches. You can get about twice as far detectability range for GRB 170817-like bursts. You can detect SGR 1935-like flares. We simulate to about 80 kiloparsecs, which is substantially farther than any other instrument, and magnetar giant flares like SGR 1806-20 out to 40 megaparsecs. So this is very important. And crucially also, the arc-minute localization, the very high effective area matters obviously for increasing your range, but the arc-minute localization is very important for 2 reasons. 1, if you localize your GRB to arc-minutes, you can rapidly do follow-up without having to do wide field searches of the localization region. But 2, also the FRB rate is sufficiently high that there will eventually be a FRB in close temporal coincidence and agreeable spatial coincidence with, for instance, a Fermi GBM GRB. You're seeing a typical Fermi GBM localization region in pink on the bottom panel. And that will be a chance coincidence. And that's just because the typical GRB localization regions are very large. And the arc-minute localizations from BAT are the only way to sort of break these and do much more sensitive searches that don't have to deal with quite a high chance coincidence rate. But we have a problem. The data that allows all of that awesome science that I was just talking about to be done intrinsically doesn't classically actually make it to the ground. The SWIFT mission was designed for prompt detection and localization of bursts, which means, in order seconds, which means the only thing that was really funded was real-time analysis. So the data had to be analyzed on board. And that meant that, despite this amazing data, one, the BAT effective area is large, so the data volume is very high. And so since there wasn't a requirement to find GRBs in anything but real time, the capability wasn't built to be able to bring all that data to the ground. The antenna that exists on SWIFT is bandwidth limited, and the onboard recorders are insufficient to record all of this data, all of this time-tagged event data, and bring it down to the ground. So all of the science that I was talking about that would intrinsically be possible for on-the-ground, targeted searches wasn't actually possible. And so the result was that for 15 years, BAT relied on its onboard real-time analyses to find GRBs. It still did, fantastic, amazing science, but the idea of targeted searches wasn't really possible, at least not to the extent that it could be. But similar to the way that there are baseband buffers on FRB instruments, this time-tagged event data is actually stored on board the BAT for about 20 to 25 minutes. You're seeing this on the plot on the right-hand side. This is the time to wrap the circular event data buffer as a function of mission year. And you see that, that the event data still exists before being overwritten for about 25 minutes. And if you can get a command to the spacecraft to save the data before it gets overwritten in the ring buffer and bring it to the ground, then you could do these sensitive searches. But the problem was that the fastest responding that was possible before last year was order 2 to 4 hours. And I would mention that this is faster than anyone else, but still not sufficient to bring this data to the ground. So we worked really hard on this problem. And the answer is something called GUANO, the Gamma Ray Urgent Archiver for Novel Opportunities. This is the first ever autonomous and on-demand commanding of a space telescope for scientific purposes. It now regularly, about 5 times per day, autonomously commands SWIFT in extremely low latency based on external triggers from gravitational wave instruments, from FRB instruments, from other GRB instruments, from neutrinos, to save the temporally coincident event level data. What you're looking at on the left is a plot of the command arrival latency on board SWIFT. And this includes all latency. So this is minutes from the astrophysical T0. So this includes the time that it takes the triggering instrument, let's say it's CHIME, to realize there's an FRB in the data, trigger on it, send us the event. We upload the command gets to SWIFT, and actually it shouldn't say command arrival on board. This is actually the execution time on board. So now we are capable of retrieving this time tagged event data. We can do the interesting science. And there's also other things that we can piggyback on it to do in terms of TOs, and I'll talk about it in a little bit. But one of the problems that we realize is that this conventional coded aperture mask imaging technique that I was describing before, where you cross-correlate your detector plane shadowgram with the mask pattern, has a problem. And that's that it has a very large image noise population. You're looking at a cumulative distribution of the number of image blips. So this would be like candidate sources in a sky image that's created via the cross correlation of the shadow mask as a function of the signal noise. And you see about signal noise of 6.5 or so. There's a kink in the distribution where it goes from signal dominated, everything above SNR of 7 is essentially real, to a dramatically noise dominated. If you do a log linear extrapolation though, you see that there are certainly real signals hiding in the data, but they're totally dwarfed and unrecoverable. And in addition, conventional imaging rejects uncoded counts on the detector, which contain information. It neglects using the energy information, and also has a lower effective area at high energies because even lead is transparent to gamma rays above about 200 keV. And so it decreases your effective area to short hard bursts. So Jimmy Delani and I worked on a totally new way of analyzing BAT event data. And this is a maximum likelihood analysis. So instead of taking the data and deconvolving it with the known mask pattern, instead we build a full forward model of the instrument and simulate GRBs through the instrument and compare them to the observed data with a likelihood test. What you're looking at on the bottom of the screen is not real data. It's simulated data for GRBs that arrive from different incident directions on the sky onto the detector plane. This highly coded region that you see on the left is, basically has all of the arc-minute localization information encoded in the rapidly changing response here. But you see that even in the non-coded region, there are shadows of mostly the spacecraft components that are cast on the detector that do have non-zero counts associated with them that contain information that you can use. And imaging totally rejects these and throws them out. And our new nitrate search uses this information to be more sensitive to GRBs, one, and to localize fainter GRBs than could possibly be localized with imaging. And the sensitivity that increase that we achieve is about a factor of 2 to 5. But the spatial parameter space to do these forward models and these likelihood searches is massive. As I said, the BAT field of view is 7,000 square degrees, and the PSF is about 18 arc minutes. So that's a lot of spatial locations to check. And we want to find these GRBs, whether they're GRBs that don't have counterpart or they're targeted searches in response to FRBs in low latency. So we've worked on a lot of intelligent spatial seeding and stage refined localizations. What you're looking at on the left is the field of view of the Burst Alert telescope projected onto the sky. These IMX, IMY units are just a tangent plane image projection. One unit in these coordinates is about equal to 40 degrees on the sky to give you a sense of how big the field of view is. And basically each circle is the location where a different GRB injection was done, and a model shadowgram like one of these produced for a GRB at that location and then compared to the data. But as I said, the PSF is actually a lot smaller than these circles. So we do a first round where we do the spatial seeding to find the best fit localization, which was going to be the reddest regions. And then in the top right, we zoom in on that region and do even more spatial seeding with different resolution grids to sort of try to converge on the best fit localization. And you see that that's what's happening first with these circles, and then with these different coarse grids in the blue dots as a function of coordinates. So these coarse grids are separated by order 20 arc minutes, and then the green dots are coarse grids that's separated by even smaller. And then eventually we converge to the red, which is the maximum likelihood position and also known to be the true GRB position for this case. And
Aaron?
Yeah.
3 minutes.
Okay, great. So that took a little bit longer than I expected. I'm sorry about that. I'm going to skip over some things. Basically, the takeaway is that nitrates is much more sensitive. This maximum likelihood search is much more sensitive than imaging. You see this here with the maximum signal noise ratio achieved by imaging on the left versus nitrates on the right. And you see this large noise population in orange from imaging just totally vanishes. For nitrates, it's suppressed, and the significance of the true GRB position is radically enhanced. The cost is a factor of 1 million in CPU time. But if you think detecting faint GRBs or SGRs or magnetar giant flares is worth it, then you might want to do this. To show you that we can actually discover real things this way, we've done external GRB searches with guano nitrates now since February 2020, and we have detected hundreds of GRBs with guano and provided unique arc-minute localizations at a rate now of about 1 per month. And this was 15% of all arc-minute localized GRBs last year. And many of these these localizations have been independently verified by at higher latency than what we're providing, or I guess longer time scale, after we provide the localization by the interplanetary network, or for 6 of those 18, we actually got the localization out quickly enough to discover an X-ray afterglow that confirmed the location. But of course, we're here to talk about FRBs. And so guano now, gets triggers on FRBs, and we've gotten about 300 FRB triggers to date from a combination of Real Fast and Chime. Real Fast started giving us triggers in April 2020. Their localizations are spectacular, but the rate is rather low. And Chime just about 3 or 4 months ago started giving us triggers for guano. We've dumped, about 220, I think, time-tagged event data files around the times of FRBs and run low latency GRB searches around plus or minus 15 seconds of the de-dispersed FRB time. We have the deepest ever upper limits on over 200 FRBs of about 2 × 10⁻⁸ ergs per centimeter squared per second. If anything like the cosmological short GRB population is present in any of these FRBs, it's ruled out. And I should say that this is essentially the deepest GRB upper limits that will be possible until they give us the new Compton. So if you want better, advocate for that. And also the most comprehensive to date. And due to CHIME's high detection rate, we'll start to probe subdominant progenitor scenarios, for instance, cataclysmic progenitor scenarios that might contribute only 1% or less to the total FRB rate within the next few months. And we've shown that if and when we find something, we can distribute that information in order a few hours for follow-up. But just to finish up quickly, as if you saw this command arrival on board latency that GUANO is achieving to bring down the time-tagged event data files for the nitrate searches, we can also now use this new commanding infrastructure to repoint SWIFT to point the narrow field of view X-ray and UV optical telescopes at the FRB location at low latency. And we've done this now for 6 FRBs landing on target in less than 50 minutes from the FRB time. Typical upper limits that we haven't found anything. Typical upper limits that we've reached are about 3 × 10⁻13 ergs per centimeter squared per second. So this is typically sensitive enough to find any GRB-like afterglow, even at cosmological distances on these timescales, and 22 AB mag in the UV. As you see from this latency distribution, we can and will get on target faster. The reason that the fastest to date was 28 minutes post FRB is procedural, and we're currently just working out the final kinks, and we should be able to regularly achieve XRT and UVAT on target at order 15 minutes post FRB, and about once per month we should be able to get X-ray upper limits at order 5 minutes after the FRB. And the trigger criteria right now are just FRBs that have less than 10 arc minute localization radius and are very bright. And this is because we want to sample exceptional FRBs that are either very nearby or luminous. I'm going to leave this up. These are the future or ongoing improvements you can expect: faster notices of GRB detections, faster TOs, public results for upper limits for public FRBs that are not MOU protected. And the takeaway should be that we're close to probing the sub% level of progenitor scenarios for prompt emission, and within a year, maybe even down to the 0.1% level. So if you have a cataclysmic progenitor scenario, we're either going to find it soon or it's not happening. And these are questions for people that I'd like some response from. Thank you.
Thanks, Aaron. Really interesting stuff, really great talk. Any questions? We have a couple minutes. So while we're waiting, I'll remind everyone that our first poster session starts immediately after the session, so on the hour. Of course, you're welcome to join at any time you'd like, but please do come and take a look. This will be on GatherTown. Jason has posted the link in the chat, but you can also find it, I'm sure, either on the website and or perhaps in Slack. And Casey has a question. Yes.
Oh, just on your second question there, I wondered if some of these peculiar fast periodicity results are particularly exciting for you to define follow-up.
Yeah, I mean, they could be. I think what I'm looking for here mostly is, things that are promptly identifiable. So, we want, if the periodicity is something that, can be put into the low latency pipelines from, for instance, real fast or chime, and that information made available at the time that we receive the trigger, which is normally like T0 plus 1 minute, then I can use it. But otherwise, I think the things to use are like, the DM, the inferred, luminosity, localization, whether or not we should do this on repeaters or just things that haven't been found to be repeat yet. Because basically, there's a huge population of FRBs to trigger follow-up on, and we only want to repoint the telescope so many times. We're happy to do the guano bat dumps, as I said, 5 times a day, but the repoints are precious, and we want to make sure that we do it on the ones that will be most valuable to possibly have afterglows associated with them.
Great. We have one question in the Q&A. I think this will be the last question. So Sandra Terveen asks, what false event rate do you find acceptable for fast triggers?
Oh, for the BAT-GUANO stuff, not repointing, I will take anything. The cost of guano, is, like, I would say if you look at this gravitational wave, the number of gravitational wave triggers we've got on the left, it's order 1,000. 95% of those are fake. I will accept, you know, anything. Pump it to me, and if we can get a command up to Swift in low latency to bring down the data and do a search, we will happily do it. It's free. It doesn't cost anything. I mean, I guess in principle, there's magical NASA accounting that happens, but it's free.
Perfect.
Yes,
I think there's
please
no better
distribute
note
your
to
prompt
end.
FRB triggers.
I think there's no better note to end this session on than send everything you have to Aaron. Well, let's thank all of the speakers again. This has been a wonderful session. And again, a reminder, please do join the Gather Town for the poster session now, and we'll see you in an upcoming session and on Slack. Thanks, everyone.